Okay. Hello everyone, I'm Xiaolei, and today I want to introduce our work about incremental image labeling where humans loop interactive refinement. And first, data is critical in the machine learning system since it's one of the core issue when we training the machine learning models. As a data-driven since machine learning is affected by the data quality, which is in turn affects the downstream work. For example, the model deployment. And this figure shows 7 main steps in a machine learning system. The researchers found that in this process, the upstream data can have a significant impact on the completion of the downstream tasks. And this phenomenon is defined as a data cascade. By exploring the impact of data problem on the downstream tasks, they propose to improve the performance of the various tasks by early intervention in the machine learning development. And the data here, the data collection and labeling as one of the important steps that impact the downstream most. So it directly determines the quality of the dataset used for training. And some recent work discusses various types of flaws in the development of object recognition benchmark datasets. They point out that noisy data collection pipelines will lead to some misalignment between generated benchmarks and real-world tasks. Some other work discusses significant difference in the classification accuracy of object recognition system, and they argue that the differences are influenced by the social economic states, culture, and language from where the image was sourced. And in our opinion, these flaws are grounded in the way the language and the perception interact. The key observation is that there is a misalignment between what computer vision system perspective from the media and the words that humans use to describe the same sources. And specifically, current dataset utilize words and phrases to label image. For example, all category labels in the ImageNet are words taken from the WordNet, and we call these labels the lexical labels. And during the labeling process, the use of the lexical labels will make a significant impact on the quality of constructed dataset. The ground truth of the dataset will be directly affected by user experience, and users with different backgrounds may give incoincident labeling results since they have different understanding to the same lexical labels and images. So this problem has been identified as a semantic gap problem. And the semantic gap is the lack of coincidence between the information that one extracted from the real data and the interpretation that the same data have for a user in a given situation. And in our work, we criticize the semantic gap problem as a fact that there is a many-to-many mapping between the information extracted from the real data and their possible contextual linguistic interpretations. The semantic gap is actually a consequence of the fact that linguistic descriptions of an image are subjective and context dependent. This is an interesting example. and the different objects, the icebergs and the ice cubes are both regarded as the ice. Okay. To address the above issues, we introduce a knowledge representation theory and approach to the process of data collection and labeling. So we propose an image labeling process with a human-in-the-loop interactive refinement and aiming to generate high-quality ground truth datasets. And here we take ImageNet as an example to explore the ground truth in object recognition datasets. And we divide the mislabeling cases into two types, including the object ambiguity and linguistic ambiguity. And we also give some examples for the above two types. And first, note that we ignore the simple mistakes caused by the carelessness of the annotators, since they are easily identified, such as the images labeled as the acoustic guitar, and in fact it's a fake guitar. It's shaped like a birthday cake. It's in fact a birthday cake, but shaped as a guitar. Like this we call the mislabeled cases. And then the example is for the two types of ambiguity. First, the object ambiguity. This type arises from the presence of multiple objects in a same image. It occurs when there is an semantic ignorance between the ImageNet labels and the label of the most likely mean object. And for example, this figure is labeled as the oboe in ImageNet and labeled as the orchestral by humans, this one. And in fact, empirical evidence from the cognitive in the psychology suggests that humans select the mean object by some perceptual attributes and then look to multi-object images, since it's usually the most variable silent. However, in the contrary, we observe that ImageNet exhibits bias from many multiple objects images. The labels of these images correspond to a distinctive object rather than the mean object in an image, making it a challenge for the models, for the machine learning models, to extract features from the corresponding categories. And then the visual ambiguity. When annotators label images, the ambiguity arises in the understanding of visual data. This is determined by the background and experience of different annotators. Images are visually polysemantic when their visual semantic are described only partially, and their interpretation is not unique, thus allowing for the use of different labels, for example, in the ImageNet. As shown in this figure, the example is labeled by the different annotators as a sports car and also the convertible, which are the same level classes in the ImageNet. Furthermore, the two similar images in this figure is the seashore and the lakeside in the ImageNet. They are also representative examples that confuse the annotators. And we summarize two design factors of the ImageNet behind such confusing class pairs. First, in some cases, the object in an image may overlap, which causes confusion with the automatic image retrieval process in the ImageNet. And secondly, it's most important for us, and it is choosing the disjoint labels grounded in a linguistic properties. This is insufficient for human to visually disambiguate confused class pairs when annotating potential overlapping image distributions. So due to the semantic gap problem described above, the results dataset may not accurately capture the ground truth, which is seriously affects the quality and the dataset. And here, to solve the above problems, we got the intuition from the real-world knowledge representation, and we also observe that the visual data and the words both can be organized as a hierarchy like this, and both the visual images and the words can express the same substance concepts. So we try to organize the substance concepts in an object hierarchy like this. And our solution is that we introduce a KR-based methodology to guide the image labeling and constitute the paradigm shift by attempting to integrate CV and KR. Instead of explicitly codifying the intended semantic via the prior knowledge, we encode them in the examples and corresponding linguistic annotators used to train the machine learning models. And secondly, during the dataset labeling, we refine the ground truth of the dataset by introducing humans into an interactive loop process and improve the dataset quality by asking humans to provide feedback and supervision. And based on the proposed solution, we introduce a two-step labeling strategy. And the step one is object localization. And the second step is the visual classification. In the labeling process, we will give the annotators continuous images. It means we will give them images one by one, and the goal is to organize the objects into a classification hierarchy based on their predefined visual features. And first, we introduce the step one. The step one is object localization. It refers to the activity in which all objects in an image are localized but not identified. This step aims to eliminate the possibility of the object ambiguity we introduced before by identifying and extracting relevant objects in the same image. And in this process, the substance concept of an object is represented by the localizing object in multiple images, which does not distinguish between the individual and the classes. Individual means, for example, like this, we can call them the oboe 1, oboe 2, oboe 3 in this image, and the classes means label the oboe. It's like this. And the key to the continuous localization of a substance is grounded in its internal core factor, which is incremental, manifested and extracted as a perspectival visual properties. This is the step one. And step two, the visual classification. The goal of the step 2 is to identify the visual properties used to characterize the objects, and then eliminating possible sources of the visual ambiguity. We predefined two sets of visual properties for objects called the visual genus and the visual differential, and then build the visual subsumption hierarchies by perceiving visual properties from the new images. The visual genus refers to a set of visual properties shared across different objects, and a certain representative object is called the genus object. And the visual differential refers to another set of visual properties. It's different from visual genus. It's exploited to distinguish the objects within the same genus. For example, we take the robust as an example. And the robust is the genus object, since it has a visual genus like the merging creatures with chorus piece. One preeminent way to visualize classifying further can be based on the visual differential. It means the presence and the shape of the cross with its different extensions. For example, this one, it means it didn't have it without claws. It's called the Stanley lobster, and this one it has has a claws, and it called the American lobster. And now we detail the image labeling methodology. This is a human-in-the-loop interactive refinement process, which includes 3 loops, namely the mean loop, the vertical loop, and the horizontal loop. And the first step we mentioned before, the object localization, is applied in the mean loop. And the the second step means the visual classification produced by the vertical loop and the horizontal loop. And in the mean loop, the top level loop, it's a top level loop. It's designed to continuously offer the images for the interactive labeling methods. In this process, the object localization steps are introduced to avoid object ambiguity. And an object localization model, for example, the YOLO V3, is introduced to automatically locate objects by machine in an image and crop the image based on the coordinates of the objects, and aiming to obtain images with a single object. And as a result, we can obtain multiple single object images from one multi-object image. And the second is the vertical loop. The goal of the vertical loop is to interactively refine the label of the input image through the layer by layer computation to label it. There is also a hierarchy that is input at the same time as the image. The hierarchy will be gradually enriched by adding nodes and samples in the current interactive process. When a new object inputs, the similarity is applied to compare the categories already stored in the hierarchy, and the category with the highest similarity is regarded as the candidates. And next, the human joins the loop to determine whether the object has common visual genus as a candidate. And if they give the answer face, proceed to compare this object to other categories at the same layer. And if the answer is true, the process will enter the horizontal loop. If none of true obtained means the object does not share some visual genus with any categories, and maybe they will label it as a new category. And maybe this is the future work we will do. And the second loop is a horizontal loop. The goal of the horizontal loop is to label the most refined category for the input object by comparing them within a domain category. And it's triggered by the vertical loop and compares the input object with the subcategories of the candidate. And the process starts from the subcategories with the highest similarity of the object, and then ask humans whether they have some visual differential. And also the answer, if the answer is false, it means that they belong to the same category, and the input object is labeled as a current subcategory. If the answer is true, the same comparison is proceed with the next subcategory. If all subcategories in the candidate has a visual differential from the input image, it means the object does not belong to any subcategory, and it's labeled as a new category, and will be added to the hierarchy as a new subcategory. And in this process, we complete the labeling and enrich the hierarchy at the same time. The incremental hierarchy will also continue to be utilized in the next top level loop. Okay. Here I give an example to introduce the labeling process. And for the annotators, you will be given a hierarchy like this, and will also give you the predefined visual genus and differential like the table shows. And we just use one image to take the example, and we need to compare the new input images with the hierarchy and follow the three loops. First, this is an image. It's just have the one object in it. So for the top level loop, the mean loop, we will directly go down and enter the vertical loop. In the vertical loop, we need to compare the images with the object already exists in the hierarchy. For example, you can see at here, if we compare with the first category, it means produce musical tones or songs. We will ask the users if this new object can produce musical tones and songs. The answer is yes. So we go down and enter the horizontal loop. And in the horizontal loop, we will continue the vertical loop to compare the images with all objects in this level one by one. And first, we can ask if the new object will they will also have the genus before. It means in this category, they have this genus produce musical tones and songs. So at here, we will ask the annotators if the images can produce sounds via keyboard. The answer is false, so we go to the next object is here. And also ask if the new object can produce sounds via the taught strings. The answer is yes, so we go down and enter the new horizontal loop, and follow the previous process and ask if they have 6 strings. Answer is yes, then we go down, and also ask if it's no input jack. Answer is yes. So this is the category the new image belong to. So the annotator will put the new image at here, and this label, the 1.2.1.1 is the label of the new image. This is an example for the image labeling process. And here we give some evaluation results. To evaluate the inter-annotator agreement, we collect 191 musical instrument images of 9 categories from the ImageNet, and here we give 2 results given by 2 experts, and the number is the image number belongs to this category. I mean it means in the category 1, the expert 1 annotate 17 images in this, and also the expert 2 annotate 17 images for the category 1. It's all the number is all the number of images in the category. And after finishing labeling, we found that for every category, the image labeling agreement between the 2 experts is very high. The Kripdorf alpha is a metric to measure if the annotators have agreement when they annotate the images. We can see that the results is it's about 98%. It demonstrates the near perfect agreement between 2 experts, and this verifies the reliability of our methods. And here in this experiment, we use the 2 datasets to train 5 state-of-the-art machine learning models, and we also use the same machine learning models to train the ImageNet subset. And it's in this subset is the dataset we collect with music instrument images, and the images is same, but the labeling is different from the 2 datasets. And during the training, we keep all parameters consistent and use the same test set. And the results of the object recognition, as shown, we can find that the accuracy of the same methods is significantly improved when trained with our dataset. And these results confirm that our dataset has higher data quality and verify the validity of the proposed methodology. Okay, so as a conclusion, I can say we propose a general human-in-the-loop interactive refinement process based on the KR methodology to generate a high-quality ground truth image datasets. And we aim to overcome some of the limitations imposed by the semantic gap problem we found in the current labeling process. And the results, we can see that we got good results and we got some improvements. And in the future, we will also focus on the construction of large benchmark datasets by extending the data labeling methodology. Okay, that's all. Thank you for your attention.
Thank you, Xiaolei, thank you for your presentation. And now we can ask our questions or to comment. If you have questions, you can raise your hand.
Is there any questions?
And I want to ask a question about, Analia first.
Hi, thank you for the presentation. I was wondering if you plan to run an experiment with more users.
Sorry, could you speak again? You mean how many users or how many what?
No, if you plan to run another experiment with more users, since
Yes,
as far
it's
I
correct.
understand.
I need more users, and in the future we may use crowdsourcing to help us for this process. Because if we want to get a large data set, we have to get many we need to collect more images and more labeling. So the crowdsourcing will help us to do this.
Okay, thank you.
Thank you.
And I want to ask a question about your actions. You have a lot of actions, like the first and the first one, 1.1 and so on, and how to operate your actions. I mean, you ask the people to act these actions, or you use the algorithm to act these actions.
In fact, these actions will be given by a tool when the users doing the annotating work. It means we will design a tool to give the actions, and the users will just give the true or false when they annotate one image.
Okay, thank you.
Thank you.
And Marcelo, please.
Oh, it's just a curiosity I have, Shole. So you are trying to define the objects as the, let's say, immediate or most common description of this. But for example, you are considering or analyzing the possibility of using more abstract ideas of the objects, like for example, the lobster that you show there, it could be food, for example. So, I mean, this more abstract idea, or this could be danger, like a lobster can kill you or something like this. I mean, this type of relation of more abstract ideas of what they mean, or like Fausto mentioned, function, actions, or the functions of these objects. These are something that you're considering, or you're keeping simple, let's say.
Yes, I think it's a good point. In fact, I also find some problems like you mentioned, because for one object, different people will give different understanding. For example, the lobster, it will be food and also an animal. But now in our data set, when we constructing the data set, we will give some clear comments when we definite the genus and differential, and this will be like organized as some principle to the annotators when they doing the annotating work. I know it's a really it's a complex work for if we make this to the annotators, but if we want to get a high quality data set, it's we have to give more details and give more like principles when they annotating. But in current stage, we didn't think about the problem you mentioned. We just think the annotators will know this belongs to animal, not food, like this.
So just a comment on that. Just be careful with leading the annotators. I mean, from a research point of view. But I don't know. You probably will check your state of the art on how this is how you can do it the best way. Let's say.
In
Because
fact,
you can your result can be, let's say, described as biased if you lead too much, let's say. But yeah, just a comment on that.
okay, thank you. I will check and find if there are some more like useful methods for this.
Yeah. Okay. Thank you.
Thank you.
Charlotte.
Is there any people want to ask questions? Andrea, please.
Yes, another curiosity. Do you plan to have some selection strategy of the image that you want that the crowd relabel, or you plan to just give all the image to the crowd and relabel every image? I mean, maybe you have some way to detect which image are probably mislabeled and take this image and ask again the user to relabel them. I don't know if clear.
I didn't get the main point. Do you mean that we use the label in the ImageNet, or you mean what? Sorry.
No. Do you plan to use all the images in the ImageNet for your experiment,
Yes.
or
Yes.
will you just
I
take
want
a
to use
subset, for example, the one that you think that probably are most mislabeled? Maybe there are some categories that are more difficult to correctly label, and so you will focus on that, or?
First of all, the images. Now we use the images in the ImageNet since it already includes most of the images we can find, and maybe in the future we will collect more images. For example, in the ImageNet and the open images and so on, like this. And sorry, I forgot the next point. Images, and next is about the
Just on if you focus only on few categories, or you plan to work on all categories
for
of
the categories.
image,
Yes,
classes, let's say some.
Yes, classes.
Yeah.
Okay, I mean for the data set, in fact, our methodology is used to provide a high quality data set, and the data set will also use like the ImageNet. For example, it can be used as the image classification, or maybe in the future we can give more labels for to do the object detection like this. Is the image the data set will do the similar work with already the data set already exists, and our dataset will also have a hierarchical, and this will be make some will be provide some I mean this hierarchy will help for the fine grained image classification like this, and we can in the future we can the users can collect some subset of some subcategories and some set from the whole data set like this.
Thank you.
Okay, thank you.
Thank you. And I think there is no more questions. And today's seminar can stop here. Thank you for Xiaolei's presentation.
Thank you all.
Bye.
Bye.